Well, guess I'll leave it there for now. Number 36. Let's see. Let's move this out of the way. 23 degrees centigrade, the vapor pressure of pure water is 21.1 millimeters of mercury. And it looks like the temperature is stable. So this is the vapor pressure of pure water. So we would say that's P0 of water equals 21.1 millimeters of mercury. Okay. If 18.55 grams of sucrose is added to 17.6 grams of water, what's the vapor pressure of the solution? All right, remember the law that governs the effect. This is a colligative property. It's Rayleigh's law. So if we want to know what the vapor pressure is under whatever conditions, whatever concentrations, then we need the mole fraction of the solvent, water in this case, times its pure vapor pressure. So we've got to figure out, we know what this one is, it's given to us. We got to figure out what that one is. What's the mole fraction of water? Well, we've got 8.5 grams, 8.55 grams of sucrose and a molar mass. So we can find out how many moles of sucrose there are. 8.55 grams of sucrose. And we want to find out how many moles that is, because mole fraction is, excuse me, for water is moles of water divided by the total moles. So we got to find out both moles of sucrose and moles of water. Excuse me. Grams on the bottom, moles on the top. So let's see, 342 grams there. And let's go ahead and calculate that one. 8.55. And let's see, divided by 342. That's 2.50 times 10 to the minus 2 moles of sucrose. Okay, so now we need water. How many grams of water? 17.6 grams of water. And what's the molar mass of water? We've done that so many times, you ought to have it memorized. 18.02. And that's 9.767 times 10 to the minus 1 moles of water. Okay, so now to calculate the mole fraction of water, let's see, let's do that over here. Mole fraction of water then would be equal to the moles of water, 9.7, let's say 77 times 10 to the minus 1. And then the total is 9.77 times 10 to the minus 1 plus 2.50 times 10 to the minus 2. And that's it. That's the mole fraction. So I got this one in here already. Let me duplicate it and then add 2.5. Wait a minute. Let's shift that down. There we go. Sure. Shift down. I can add these two together. No, that's not going to work. Let's try it again. And then 2.5 exponent is 2. Add those together, then I can divide. Okay, this mole fraction is 0.975. So we fill in the values here for Reynolds law. Mole fraction is 0.975 times the pure substance, 21.1 millimeters of mercury. 21.1 times. So I get 20.6 millimeters of mercury. Okay. This might be quicker. Just leave some ghosting on the board that I'll have to deal with. Okay. 37. Okay. Excuse me. When delta G zero for a reaction is less than 0, the value of K is what? Well, you might have this one memorized, or you may want to go to the formula. Delta G zero equals minus RT log. Is that natural log? Yes, natural log of K. Okay. So if this is negative, what would keep this one negative on that side? This would have to be positive. Right? It's that simple. Greater than 1. In other words, it's positive. Right. 38. In which case is a process non-spontaneous at any temperature. All right, for this one, you need to go back to Gibbs law, Gibbs equation. There we go. So we're looking for non-spontaneous at any temperature. I mean, this has to be positive to be non-spontaneous. What would be any temperature? Well, make this one positive for sure. And what would keep this one positive also? If this is positive, if this total is positive, then any temperature times a negative would give you a positive value. So delta H would be positive, delta S would be negative in order to satisfy the conditions of that problem. 39. A flask initially contains 0.1 molar nitrogen, 0.24 molar oxygen, and the KEQ constant for the reaction is 4.08 times 10 to the minus 4 at this temperature. Equilibrium concentration of oxygen would be what? Well, we know that we need a balanced equation to govern this reaction. Okay. And this is in equilibrium with 2NO There. What else are we given? KEQ, 4.08 times 10 to the minus 4. Right? Excuse me. And the concentrations, the initial concentrations of nitrogen 0.1 molar and oxygen is 0.24 molar. Like that. And this one is 0. Those are starting conditions. Okay. What kind of change are we going to see? Well, we're going to lose some of this. We're going to lose some of this in equal amounts. Well, we want to know the equilibrium concentration of O2. That is, we want to know this value right here. Okay. So if we let this one be X, then, and we lose X here, then that will give us an expression. Well, we can't let this one be X. This one has to be 0.24 minus X. And since they're 1 to 1, they're the same values here. This is 0.100 minus X. What's this one? This one's plus X. So that's X. Excuse me. All right. So for KEQ, the expression then is NO squared over N2 to the first power times O2 to the first power. And that's equal to 4.08 times 10 to the minus 4. So if we put these values in our expression, NO is going to be X, and it's going to be squared. And then the denominator is 0.100 minus X times 0.24 minus X. There we go. All right. So what we're going to get out of this is a quadratic. The question is, can we logically reduce these values to nothing, to 0, to discount them? Well, let's see. How much of this are we going to get if this equilibrium constant is 10 to the minus 4? There's not going to be very much X lost on either side. So we should be able to estimate saying X squared over 0.1 times 0.24. And then solve for X. Oh, anybody catch my mistake? Ratio 1 to 1 to 2. We lose one of these here, we gain 2 of those there. So this is 2, and this is 4x squared. Okay? Details get you every time. So 0.1 times 0.24, and then that over here times 4.08, 10 to the minus 4. So what we have so far is 4x squared equals 9.792 times 10 to the minus 6. And x is going to be the square root of, we're going to divide this by 4 and then take the square root of it. So this gives us 2.448 times 10 to the minus 6. Take square root of that. And I get 1.56 times 10 to the minus 3 molar. And why is that wrong? Let's see. What calculations did I do? Okay, these are correct. This is correct. Did I write the equation correctly? Yes. Okay. So we got start off with this amount, none there. Minus, plus 2x, bring 2x, 2x, 2x. Okay, so that's fine. Oh, I'm not finished, right? I'm not finished yet. This is x. 0.24 minus x. So 0.24 minus that value is 0.2. Well, it's about 0.24, 0.238. So this is equal to 0.238. There you go. You have to finish the problem. All right, next. It must be number 40. All right. Determine the reaction order with respect to C for the reaction A plus B plus C equals products, given the following table of initial rates. Okay. This is an initial rates experiment. And if we write out the law, the rate law, then we have yeah, M to the little m, and to the little n. Oh, excuse me. No, we don't. We have A and B. A and B and C. So I want to put O. No, I don't want that. I want to put P. There we go. So this is the entire rate law, but we're only interested in the order with respect to C. So what we have to do is, excuse me, this is the rate expression. So which of these two rate experiments, initial rates experiments, will allow the concentration of C to change, but A and B remain constant? Looks like the first two. The first two will hold these constant and let this one vary. Okay. So let's put the second one on top simply because the ratio after that will give us a whole number rather than a fraction. So the rate of the second experiment is equal to whatever K happens to be. And it really doesn't matter what K is. And it doesn't matter what A is either. Well, let's put the values in there just to be complete. Right, so A is going to be 0.1 to the M, and B is going to be also 0.1 to the N. And the second one gives us C is 0.2 to the P. Okay, and this rate, this second rate, is equal to 6 times 10 to the third. Okay, so now we're going to ratio this with the rate for the first experiment. And that one is 3 times 10 to the third. Okay, you got the same things here because we chose them that way. And the value here is 0.1. Okay, so these will cancel, 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 cancel. And then what we have left over is 0.2 divided by 0.1 to the p power. Right? So that's 2 to the p. All right. And this one divided here is 3 into 6 is also 2. So what does p have to be for this to be true? P has to be equal to 1. Right? So the order with respect to C is first order. C equals 1. P equals 1. Okay. Well, we could do that with any of the others because we have a complete set of data. Right? If we wanted to find out what A is, then we would have to say B and C must remain constant. And that looks like the last two experiments would give us A. And I'll be willing to bet that A is 0 order. And B, if we wanted to do B, then we'd have to let B change and A and C remain constant. So let's see, how about B would change, A and C would be constant. First one, no. Second and fourth. Yeah, second and fourth would be used for B. All right, that was 40. Let's see here, 41. So 41, let's see. It'd help if I read the problem. Which acid is likely to result in the greatest percent ionization in an aqueous solution? Greatest percent ionization. Well, these are all the same concentration. So the K, if we just take a generic, say HA, is going to yield that plus that. And A can be any of the conjugate bases derived from those acids. They're all the same concentration. So our expression here, Ka equals H over A minus is HA. And percent ionization then is going to be, let's use, since they're 1 to 1, it doesn't matter. How much is this is lost? And we can say in this expression is, say, concentration of H plus, and then what was the original concentration? Times 100. Right? So what's going to govern the values of this one right here, this one? The K value, the Ka, and look at that one, that's C. It has 2 Ks. The question is the second K going to have an impact on the overall? And the answer is no. Because the difference between the first K and the second K is about 10 orders of magnitude. So the second K we can ignore. And we can just, since they're all the same concentration, we just compare the Ks. Yeah. So the one with the largest K value is going to be dissociated the most at the same concentrations. So percent ionization is going to be proportional to the K. The largest K will give us the largest percent ionization since they're all at the same concentration. So that means A, whatever that acid is, HC2H2, HC2H2, BrO2, BrO2. All right, this is your acidic hydrogen right here. These don't count. Those are locked in place. So this one has the largest K. It will also have the largest percent ionization. All right, 42. Methanol can be prepared by the reaction below, CO plus H2. CO plus H2 yields what? They put it in equilibrium format. Methanol, that, and we need two of these. Right? Four hydrogens, one carbon, one oxygen. Okay, we're good. We're balanced now. By this reaction, the equilibrium concentration at 250 degrees were found to be 0.960, 0.0960, right? Yeah. And hydrogen 0.191 molar, and 0.150 molar. All right. It says these are equilibrium. Right? So what's the KEQ for this reaction? It's simple, very simple calculation. Right? We want the methanol on top to the first power. We want the carbon monoxide in the denominator to the first power. And we want hydrogen to the second power. Well, I should put the numbers in there, shouldn't I? Kind of mixing apples and oranges. So this would be 0.150. 0.150, enter 0.0960, divide, and 0.191, square it first, then divide. And that gives me 42.8. Right? 42.8 is the K for that reaction at that temperature, 250 degrees Celsius. All right. Scroll to the next one. 43. Okay. How does this change in stoichiometric coefficients affect the equilibrium constant expression? Right. Well, let's see. We start off with methane, which is a gas, and we have two waters added to it. And it's in equilibrium with carbon dioxide. Yes. And 4 hydrogens. Yes. Okay. And if we say the Kp equals X, then what's the expression for Kp for this reaction if we change the coefficients? If we change the coefficient to 2, 4, 2, and 8. Right? All right. We can go through the procedure for calculating this one, then calculating expression for this one, and comparing the two. But remember the rules that I gave you at the beginning. If you multiply any value here, let's see, you can't use X, let's use, I don't know, A. Multiply the whole thing through by the constant. What does that do to the change in the expression? This constant then is multiplied by each one of these. And that becomes the power multiplier for each of the terms in this expression. We can factor that value out because it's the same multiplier for each one. Factor it out. And this factored out, what was it? We multiplied by 2. Right? So that means the KP new is equal to the old KP squared. Right? The multiplier becomes the power. Number 44. All right, a buffer solution consists of 0.1 mole of acetic acid and 0.1 mole sodium acetate in 1 liter. How much will the pH increase if 0.01 mole of sodium hydroxide is added to the solution? Assume that the volume remains constant. Okay, we have to make that assumption, otherwise it complicates the calculation considerably. All right. Did we do this one already? This one sure looks familiar. Let me get my hard copy and see if we have already done this one. I may have duplicated it. If not, we'll do it. I'm just thinking that it might be a duplicate. Okay, maybe not. We'll do it again. So, the reaction that we're looking at here is acetic acid, right? And we're going to simplify it and leave the water out. And this takes hydrogens and acetate ions. Oops. What am I thinking of? H3O2 minus. Okay. So what are the initial concentrations here? The initial concentrations, because this is 1 liter solution, 0.1 mole of acetic acid, 0.1 in 1 liter is 1 molar. And then 0.1 is the same. 0.1 acetate, 0.100 molar acetate. Initial. Okay. And this is approximately 0. This is going to overwhelm whatever hydrogen ions are in the solution due to just the pure water itself. So what change are we going to get? Well, if we consider this 0, then this is going to be decreased by a certain amount, like minus x. And this is going to be plus x, and this would be plus x. And at equilibrium, wait a minute, was I given some more information? Oh, how much will the pH increase if 0.01 mole of sodium hydroxide is added? So 0.01 mole, 0.01 mole of sodium hydroxide is you know what? This could work, but I think, let me modify this just a little. This would be an acid equilibrium. Let's do it as a titration. I think that would be I think that would take us there with more certainty. So this is going to give us water and C2H3O minus. There we go. So we're going to start off with 0.1 mole here because this is the buffer is already established. And we're going to have yeah, this is before the reaction, 0.010 mole. Yeah. So this is going to completely react, 0.010 molar. That gives us 0 here. And 0.010 molar is subtracted from that because it has to react 1 to 1. This is 0.090 molar. Okay. And what it's going to do on the other side is produce plus 0.010. So this will be 0.110 molar. So now we have equilibrium values for the acid and the conjugate base. Now we can use Henderson-Hasselbalch. pH equals pK plus the log of the conjugate base, which is C2H3O2 minus divided by the acid at equilibrium. There we go. So what we need is the pKa. We got 4.74. And then the values for the numerator would be the conjugate base. And the denominator is acid. Okay. So now, take this ratio and get the log of it. And take the log of that. So I got 0.087 plus 4.74, and that's 4.83. All right. I'll read the question again. How much will the pH increase? Okay. The pH, I was already there when I had this part of the equation. So 0.11 and 0.09, and then take the log of that. Okay, so it would increase by this amount, 0.087. There we go. It always helps to read the question more than once. All right. 45. Let's see. Did somebody show up while I was talking? No, I don't think so. Yeah. Yo, okay. Jada. I missed Jada. Okay. The only one missing now is Ann. Okay. 45. Which chemical equation has KEQ equal to KP? We want the equation that gives us KEQ equals KP. Well, the expression for that is in useful information. How do you change one expression to the other? And that is RT delta N. Kp equals K EQ RT to the delta N. Let me see if I got that right. 45. Yep. So, under what circumstances would this one be equal to that one? When this expression here equals 1, right? Assuming the temperature didn't change and R is a constant, then how would you get 1 out of that expression when this is equal to 0? When the change in moles of gas on either side is equal to change in moles is 0. So in other words, if the product number of moles are exactly the same as the reactant number of moles of gas, then you get this 0 change, and those two expressions are equal. So which one of those is it? Well, I've outlined it already, but you can look at the first one is 2 moles reactant, 2 moles product. Second one is 2 moles reactant, 1 mole product. Third one is 3 moles reactant, 2 moles product. And the fourth one is only the gas in there is 3 moles of gas and no gases product. So there are changes in delta N for B, C, and D, but not for A. So A is the one reaction that will give you equal values for both. That this one is equal to that one. All right, 46. Which change decreases delta G for the reaction for the following reaction? Okay. Let's put the reaction up there first. N2, it has to be a gas. 1/2 O2, also a gas. And then we end up with N2O gas. Yeah. Okay. Which change decreases delta G for the reaction? We want to decrease delta G. And if you don't write a 0 in there, that's delta G under whatever conditions are available. Well, we know that delta G, the expression for that calculation would be delta G equals delta G0 equals delta G0 plus RT log Q, correct? Yeah. So, well, we might be able to eliminate some of them, right? What if you add a catalyst to the system? That won't change the free energy. It'll change the rate, but it won't change the free energy. We're talking about equilibrium here, right? So A, we can just throw A out. Now we can look at the other three. Decrease the partial pressure of N2, decrease the partial pressure of N2O, decrease the partial pressure of O2. All right, so if we look at this expression, to decrease, how would we decrease this value, right? If this is under standard conditions and we have the conditions here, how could we decrease this one? Is the temperature constant? It doesn't say. It only references these values. So we have to assume that the temperature is constant. So if this is constant and that's constant, then we have to vary this one to give us a decrease in this value. Right? So what would make this one negative? That would have to be a negative value to decrease this one. Right? What value of Q would give us it would have to be well, let's look at it this way also. if this were K, right? If this were K, then that one would be 0. And then delta G0 would be equal to minus RT log Q, log K, excuse me. Well, if we compare let's write the expression. What would Q look like? Right? Q would simply be the concentration at whatever time of that one, and then N2 to the first power, and then O2 to the 1/2 power. So if we are in order for this value to be negative, because that would decrease the sum of the two. In order for that to be negative, Q has to be less than 1. That's just the nature of logarithms. Q would have to be less than 1. So how would we get Q to be less than 1 from wherever it is? Right? You could either increase N2 or O2. That's not an option. Or you could decrease the numerator, decrease N2O. That's why C is the answer. Right? Decrease N2O. That sends this one negative, and that translates into a decrease in delta G, decrease in free energy. Right, 47. Excuse me. Oh, for this galvanic cell reaction. Okay, this is the complete reaction. We haven't separated into half cells yet. We may not have to. We're going to see about that. The Nernst equation implies that the galvanic cell will have a more negative voltage if. All right. So for 47, if we're going to use the Nernst equation, we have to know how many electrons, how many moles of electrons are being transferred. So let's figure that one out first. Let's see. Let's move this over. Give us more room. 3HNO2, HNO2, and it's all aqueous, so I'm going to leave that out. And then we have BrO3, 3 minus, and then we have 3H pluses. So we know this is in acidic solution, 3NO3, NO3 minus, and the last one is Br minus. Okay. So we got to track how many electrons are moving. We need to know oxidation states. Right? This is -2, so -4 total, and this is +1. So together we have -3. That means this has to be +3, right? Okay, how about this one? -2, -6 total, hold one out, -5, so this is +5. Hydrogen's not going to change. Br, that's -1, so we know that changed. How about nitrogen? Over here? -2, -6 total, -5 to hold one for that one, +5. Okay. Now I'm going to draw some tie lines. This nitrogen went from +3 to +5, which means it had to lose 2 electrons per nitrogen times 1. Oh, excuse me, times 3. Pardon me. Times 3 nitrogens equals 6 electrons. Okay. Bromine went from a +5 to a -1. How do you get there? Well, if you add 5, you get to 0. If you add 1 more, you get to a -1. So this is a gain of 6 electrons per bromine times 1 equals 6 electrons. So N for our Nernst equation is equal to 6 moles of electrons. All right. So now let's look at the Nernst equation. Let's see. And we're going to use the reduced form. E equals E0, and I have to look it up too, 05916 minus 0.05916 over how many electrons? Moles of electrons? 6. Okay? And the rest of the equation is log Q. Okay? Now, we can't calculate Q, right? Because we're not given any values. I mean, we could write out the Q expression, and let me see if that's going to make a difference. All right. The Nernst equation implies that the galvanic cell will have a more negative voltage. How do you get a negative voltage here? A more negative. Move it toward the negative. Take this one and subtract. That will make it more negative. This has to be greater than, well, it has to be a negative value. This whole thing has to be negative in order for this one to be decreased. Okay, so how do we get there? Well, we can't change this one. These values are fixed, so we're focused on the Q, right? How do we get a more negative value there? Well, if we have products, right? Products divided by reactants, right? And we want to decrease Q, make Q smaller. If we make Q smaller, then the log of that is going to be more negative. Oh, excuse me. That value, right? Okay, there's a sign right there. That means Q has to be bigger. We got to make Q bigger in order to make the negative larger and reduce this one. Everybody follow me? It's all based, this is the culprit right here. That means Q has to be bigger, means this has to go up and or those have to go down. Right? So if we increase the pH, that would decrease this size, decrease the products. That's not going to do it. Decrease the bromide, right? That's going to make this smaller. That's not going to do it. We got to make this one bigger or the reactant smaller. So increase NO3, that will work. Like increase NO3. Increase BrO3. No, that makes the reactants bigger instead of smaller. Okay, so the only one that works is make nitrate ion concentration higher. And that will translate into a larger Q, which will make it more negative, which will decrease the voltage in the cell. All right, 48. Let's see. A drug is metabolized. 48. Drug is metabolized in a first order reaction with a half-life of 4.12 days. If a patient ingests 100 milligrams of this drug, what mass remains after 30 days? So first thing I notice is that the units of the time are consistent. Half-life 4.12 days, and we're looking for 30 days. But in order to work this problem, we need to know first order. So first order half-life is, we need to know, all right, let's work backwards. If we're going to find out the final concentration, we need the integrated rate law. And the integrated rate law for a first order reaction incorporates natural log. Natural log of, it doesn't give the drug a name, so we're just going to say A. So that concentration, natural log of A, equals minus KT minus KT plus log of A, 0. Starting concentration. Or starting, yeah, starting amount. Okay, so we need to find out what K is. This is a first order reaction. So the half-life we're given as 4.12 days. And that's equal to the half-life expression for a first order reaction is 0.693 over half-life. So K, K is equal to 0.693 over T 1/2. Right? So that way we can solve for K. We just need to put the half-life in here, equals 4.12. So that calculation will give us the K value, 0.693 and 4.12. So this is 0.1682. All right, so we can put that in this equation, minus 0.1682, and the time it takes is there. Right? That's what we're looking for. Excuse me. No, 30 days. Sorry, my fault. 30 days. What's the initial concentration? Well, 100 milligrams, right? Since the size of the body is the same at the beginning and the end, so the concentration is going to be proportional to 100 milligrams. And this is log A. So what we need to do is solve this side and then resolve the log. So let's see. I've already got that value in there. I'm going to change the sign times 30. And then 100 natural log and add that to it. So this is minus 4. Well, let's see. I can put it standard notation. 0.440. Yeah. All right. So what's A? A is equal to E to the minus 0.4409. So I just take it like that. And this is 0.643. And the units here are in milligrams. Close enough. Best answer here is 644. Must have been a rounding error. Okay? All right. Next. Yeah, we're good. 49. Excuse me. For the reaction, A gas yields B gas. A gas yields B gas. Q is 15. We got Q is equal to 15 and K is equal to 5.5, correct? Yep. What statement is true? Delta G and delta G standard conditions are both negative, both positive. One's negative, the other's positive. Okay. Let's look at we might let's see, two equations. Well, we know that delta G equals delta G0 minus RT log Q. And if we're at equilibrium, then this value is 0. And now delta G0 equals RT log K. Right? This is anytime, preferably not at equilibrium, and this is at equilibrium. So if delta G is positive, delta G0 is or positive or negative, or both positive or both negative. If this value here is negative, then the forward reaction is favored. If it's positive, the reverse reaction is favored. So under these conditions where this is bigger than that, what does that mean? Well, Q means that there's too much B and not enough A, like compared to those two. All right, so if Q is bigger than K, and we're looking at this reaction, then Q is really large. It makes this more negative. Makes this value more negative, right? That's more negative. Yeah, let's see. Yeah, that's another way of saying it. This whole value is more negative. Then what does that do to the G versus the delta G? Well, if this reaction is 5.5, that means the delta G is negative. Delta G0 is negative. Delta G0 is negative. If this is big, like that, I think that's. Did I write that correctly? Let me check my values here. No, it's minus RT log. Minus RT. And the other one should be, it's probably a plus. Okay, I messed up. Let me look at my formulas, get that straight. Yeah, I messed up. That's a positive. So let's back up. Let's go back to these values. If we're looking at delta G, then we have to use this equation. And this is a very large value. It's a very large value, which means that delta G is going to be positive. Right? With this value being large, put it in here. That means this one has to be positive. But with a K of 5.5, put it in here, then that makes this value negative. All right. So delta G is positive, delta G0 is negative. And we also know that if K is greater than 1, then the reaction is spontaneous from left to right, which means delta G is negative. And this is where it came from. So I went around the barn 2 or 3 times to get where I was going because I made a mistake on the way. But if we use this equation for Q and this equation for K, we can assign positive, negative for each one. Oh, that's it. No more. Oh, I'm sad. Oh, well, that's all I had marked off. Unless you saw something in the review document that you want to tackle. Oh, we did every one though, didn't we? Yeah. Well, then, any other questions? If anything else doesn't make sense to you, then this is the time. Otherwise, we finished the review, and the syllabus schedule has next Tuesday assigned for a review, but we don't need it. All right, so the final exam will be open. In fact, I think it's open now, and you can take the final exam in Brightspace, or if you're in the neighborhood, you can stop by. I'm not going to come into the classroom on Tuesday or Thursday, but my office is 129, just down the hall. And if you decide to come and take the exam in person, just come to my door and I'll set you up. Otherwise, I'll be looking for your completed final exams in Brightspace.